This is joint work with my co-author Justin Sirignano from the University of Illinois. And as you can guess from the title, it's about deep learning applied to intraday data. Now, this is not a new topic. Many people have been trying to apply neural networks to financial data, and not just recently. Since the 90s. In the 90s, there was a period where there was a lot of activity around neural networks in finance. People tried to use neural networks for forecasting. And there are thousands of papers probably on this. And globally, if you look at the results, they were mediocre. They didn't work. The results were quite poor if you compared them to, simpler statistical techniques, which are very explicit, so you understand exactly what's going on in the model. It didn't seem like neural networks in the 90s were really competitive with respect to other techniques. Now, so then people abandoned it for pretty much 15, 20 years, and there has been a resurgence of activity in the recent years with the advent of computational power, large data sets, and deep learning, which is a result of this. So I'm going to revisit this, and I'm going to show you that really these techniques are only interesting if you apply them to extremely large data sets, and you need the computational power that we have now to train these networks. I will show you. It's an extreme example of how much data and how much computational power you need. But when you do that, when you have that data and when you have that computational capacity, the results seem very interesting. So this is what I'm going to try to convince you. So I'm going to talk about price formation mechanisms related to intraday market activity. So we have now in electronic markets, so most stock markets and future markets now are electronic, you see buy and sell orders streaming in every microsecond in the most liquid markets, in milliseconds in most of the markets. And so you can see the supply and demand evolve in real time, which is really a unique case in any market. And then you see the evolution of the price following this evolution in supply and demand. So most of the markets are organized through a central limit order book. So you post buy and sell orders at a given price. And these orders sit in something called the limit order book. I will show you an example in a few seconds. And then the order book matches the buy and sell orders, which can be matched, and the price evolves. The price is updated. And prices are updated several times a second. So we understand the rules by which these orders are matched. We can model statistically maybe some of the order flow, although it's very difficult at these high frequencies. So in principle, if we can model this order flow and we know how the orders are matched, we could deduce how the price should change when a new order flow arrives. So in principle, but actually if you want to do it quantitatively, it's very difficult. So that's what's called the price formation mechanism. So the price formation mechanism is the mechanism through which the price reacts to a given flow of supply and demand. And you can think of it as a function which maps the previous price, the order flow, to the next price. Okay, so I wrote this function here. So it's price at the next step is the current, is a function of the price history and the order flow. Okay, and the order flow itself reacts to the price history. It reacts to the order flow itself. So people look at what's happening to the order book. They react to it. They send orders because the prices move in such and such way. Moving averages, more complicated. So there is a lot of path dependence probably in this function f. Okay, so that's the reason for which it depends on the history. Now, you can think of all econometric modeling, market structure modeling, stochastic models of intraday behavior as some ways to model this function f, more or less complicated ways to model this function f. And that's also what we're interested in here. Okay? So some questions that are interesting to ask at the very general level are, okay, so we have this function f, which we call the price formation mechanism. which maps order flow and price history to the next price, is it specific to each stock or is it universal? I mean, that's a good question, because if you look at the theory, you don't have a theoretical literature on price formation in stock markets, price formation in bond markets, price formation for IBM stock, Google stock. It's an abstract model, so people implicitly assume it applies to everything. Is that true? Is that empirically supported? So this is a very simple question. And then the other thing in practice is this map F stable in time, or does it change, from this year to next year, or if you go back 5 years, is it the same map? Well, again, the theory assumes it's the same because there's no explicit incorporation of time effects. Maybe there are some intraday effects which are easy to incorporate, like seasonality, but explicitly time doesn't feature in these models. But practitioners always tell you, oh, it's non-stationary, be careful, you cannot use old data, it's useless, you can only use the last week's data because otherwise you're forecasting useless stuff and so on. So it seems that practitioners really think it's non-stationary, and they advise you against using old data, and in high frequency, old means last week. I mean, they should tell you, don't use more than like a couple of weeks, or more than a month is just totally nonsense. Is it the case or not? So we want to understand whether this map F is universal across stocks, and is it stationary across time or not? Now, of course, you can test this with a statistical model. If you have a parametric model for F, you can fit it and see if the parameters change in time, if the parameters change across stocks. But if you reject this, then you don't know whether you're rejecting your model or whether you're rejecting stationarity and universality. So typically you will reject it if you use a model that is not flexible enough, but you don't know why you're rejecting it. So it is of interest to answer these questions non-parametrically without assuming exactly what F is too specifically, or at least having a very flexible F which can accommodate many features. So that's where it gets interesting for us, because there is lots of data. As I said, for liquid stocks, we have microsecond information on this order flow, and this means petabytes of high-frequency data on transactions, orders, cancellations of orders, etc., per week. So for each week, we have petabytes of data, and if you, this is for one stock, okay? So in principle, if you have so much data and you want to estimate this function, if the function is really something that is stationary, you should be able to recover the main features of the function in some way, and that's where the machine learning techniques can be potentially helpful, okay? Now, there are, again, even in the recent literature, there are lots of studies involving machine learning, and in particular deep learning, applied to high-frequency data. But if you look at them, they always look at one contract, one stock, one futures contract over 1 day. And in fact, if you look at the standards in this literature, in other fields, okay, 1 day of transactions looks like a lot. There are millions of orders and transactions in 1 day. But if you limit to one stock in 1 day, it's actually not that large, considering, and I will show you later, the number of parameters involved in these neural networks. It's really not that large. And the conclusions of these studies are not great. Typically, so most of the papers they apply some neural network for forecasting method over a few days to some stock. They show you some graphs, and then conclusion, finished. It's 6 pages, because in these conference proceedings, you're limited to 6 pages. It's convenient because you don't have the time to discuss really what's going on, and often you don't know what is going on because you don't benchmark against other methods, and it's hard to see whether it's a good result or not. Okay, so now I'm going to show what the data looks like. So what we have is a snapshot at each observation time of the limit order book. So it looks like this. So you have outstanding orders with prices and sizes. So for example, here it means that somebody wants to sell 200 shares at price 80.03, and they want to buy 400 shares at price 79.96, and so on. So the blues are buys, the reds are sells. And this is the state of the supply-demand, if you want, at time t. And then every millisecond, there are some new orders which come in. They get executed against this, so the state evolves. So we have time series of this. And we have time series of this for all stocks on the exchange. So what I'm going to present is the NASDAQ exchange. So for all stocks in this exchange, which is around 1,000 stocks, we have this time series of these limit order books at every tick, which means every time they change. So this means typically at least every millisecond, sometimes by microsecond frequency. So what can we learn about this, about price formation? If I give you the time series of the supply-demand curve, can you learn about price formation from this? So if you think about it from an abstract point of view, okay, you have, this is a supervised learning problem. You want to learn some high-dimensional function, because this, okay, I show you only 4 levels on each side, but in fact we have up to hundreds of levels. So you have 100 blue levels, 100 red levels, let's say. This means 200 levels. And you have prices on each. So it's a vector of dimension 200 for each millisecond. And then you have this for all stocks. That's the kind of thing we have. So it's a high-dimensional input. And you want to map this to the price change, which is either up or down, or maybe you can say up 1 cent, up 2 cents, more than 2. Okay, so it's you can think of it as a classification problem, classifying it into up, down, and then maybe up more than 1 cent, down more than 1 cent. So the problem is the data dimension is large, and you have absolutely no idea what this f looks like. So a typical approach, a classical approach, is to represent this f by a linear combination of some basis functions and then do a regression, a linear regression on data. And the problem is, well, if you're in high dimensions, first of all, you need to know very well what the functions should be, otherwise you're going to have a problem choosing the basis. And then you have the curse of dimensionality, which means that to get a given accuracy, you need a number of functions typically, which is exponential in the dimension. So the approach of neural networks is really quite different. It's very far from a linear representation, and I think from a mathematical point of view, it's really linked to old work by Kolmogorov and Arnold in the 50s. So the idea is that instead of representing a function as a linear combination, you represent this function as a linear sum of compositions of functions. Okay, so you combine linear combination with the composition of functions. And so, okay, there are many ways to formulate this. This is not the formulation in Kolmogorov, because it was a bit less rigid. But basically, you fix some nonlinear increasing function phi, which is for example, it can be, but the function we will use in the examples is 1 over 1 plus exponential minus x, something which goes from 0 to 1. It can be the max. Then you combine, you compose this function with affine or linear transformations of the data, which are shown here. And so, again, in the general theorem of Kolmogorov, these were Lipschitz, but in fact, we will take them to be linear, okay? And so what was shown in this literature, and here I cite several references, there are various versions of this theorem, the Kolmogorov representation theorem, which shows that you can represent high-dimensional functions, so f is a function in high dimensions, as a combination of composition and linear combination of one-dimensional functions. So these here, this phi here is a one dimension, it's a scalar function, and the only thing you do in high dimensions is linear combination. So that's the idea. And this applying linear combinations is easy, so you need to estimate the weights of these linear combinations, and then you can represent or approximate at least high-dimensional functions in a flexible way. So now I'm going to go into more detail about this. So we fix some monotone increasing function going from 0 to 1, phi. So in all the examples, I will use this. And in fact, the theory shows that the choice of this function is not very important. You can choose whatever you like. In the literature, you either choose this or you choose a max of x and 0, which is not smooth, but it doesn't matter. And now you generate functions by doing this. You do an affine transformation inside, and then you apply phi, and then you do a linear combination outside. Okay? So you have weights inside and you have weights outside. Okay? And the idea is that by doing this, you generate a family of functions which, by composition, can approximate an arbitrary continuous function. So I'm going to now go into this. Now, where do neurons come in? Well, this corresponds, the elementary operation I just showed you corresponds to a simple model of a neuron, as you find it in the mathematical biology literature. So the idea is that a neuron is composed of synapses. So you have dendrites which connect to other neurons. So these synapses receive electrical signals from the other neurons. And then these electrical signals go into a central axon, which is like a central wiring system. And as they join the axon, it's like wires which join a single wire, the currents add up. So there's additivity here of the electrical currents. So what this unit does, it just sums the inputs. And there may be a bias here. You may shift it. It may be an affine transformation, not just a linear transformation. And then if this signal, if the electrical signal in the neuron is stronger than some threshold, it activates the neuron. It triggers an output, which is also an electrical signal. And so this activation function here basically compares the signal to a threshold, and it gives you 1 if the signal is higher than threshold and 0 otherwise. And the function we chose here is a smooth threshold. And then it generates the output. So that diagram summarizes the function shown here, but it decomposes it in a nice way into input, summation, activation. Okay, so this is what you call a neuron in this neural network terminology, and you can see that it's entirely parameterized by the weights attached to the inputs. These are called synaptic weights, and the choice of the activation function phi. Okay, and the interest of this construction comes from the fact that you can approximate any continuous function. And in fact, in the more recent literature, it can be shown that you can approximate any measurable function by appropriately choosing the weights in these neurons. Okay, so this approximation theorem, there are many versions of it. They keep improving. So here's one version due to Hornig and then Kurkova, H. Nielsen. So if you take an n-dimensional function and you fix an activation function, so you're not trying to estimate the activation function, the only free parameters are the weights in the neurons, then you can show that there are functions, so each L phi, let me recall, L phi is a neuron, one neuron, parameterized by some weights. So it's a function of this form for some choice of weights. So there exist neurons with the different weights attached to them, such that if you compose these neurons, then this gives you an input-output function which approximates your n-dimensional function f to arbitrary accuracy. And what is shown here is exactly can be represented in terms of our neurons as a two-layer neural network. So you take your data, you send it to each data is processed through one neuron, and then you send it to a hidden layer, a next layer. So this is the composition, and then the output. Then you sum the outputs. Then this gives you an output. Okay. So this is exactly a two-layer neural network. So this theorem says a two-layer neural network with sufficient number of neurons inside each layer can approximate any continuous function in dimension n. n is the dimension of the inputs here, n is the number of input cells, and here the number of layers can be actually 2 if you have enough neurons in the hidden layer. So that's a kind of approximation theorem. Now, more generally, you can have networks with more layers, and it's called deep. So deep means more than one, basically. And the theory there is lacking. We don't really understand why. I mean, so this theorem is, I showed you it works for one hidden layer, but it doesn't give you an upper bound on the number of neurons you need in the hidden layer. There's some number k. But actually, from a practical point of view, what people have observed is that if they add more layers, it's much more efficient than adding neurons in one layer. Okay? So this means that we represent the function in this form. You do a composition of the linear combination, the function phi, linear combination function phi, and so on. And you have many compositions as opposed to many linear combinations in one layer. Okay, so this is what is a deep neural network. Okay, so it's just a way of parameterizing functions, but through alternating composition and linear combination, composition and linear combination. Okay. Now, these constructions are, you can think of it as very, some kind of parameterization of functions involving weights in each layer. So every time you add a layer, you add a neuron, you have to learn the weights, and the weights are vectors in dimension n if your input is dimension n. So this means that if you have k layers and m neuron per layer, you have k m squared weights, which can quickly increase, for example, if you have 100 layers, 100 neurons per layer, then you get something which is 1,000,000 weights, which is so this is a number of parameters that you need to estimate or learn. So, and the idea in this literature is to learn the weights by minimizing some loss function. You have a large data set and you match the outputs in this data set, the relation between input and output, and you minimize the weights to get the best fit in sample. And this gives you some estimation of the weights through optimization. So that's the idea of supervised deep learning. And here all the ideas of, so this is typically an ill-posed problem. You need to do regularization of your optimization and so on. So there's a lot of technical issues involved here, but that's the idea of supervised deep learning. But you can see immediately that it only makes sense for very large data sets. If you have 100,000 observations and you have 1,000,000 parameters, well, there's a little problem there. You may overfit very easily. You may be able to fit perfectly in sample, but the extrapolation out of sample may be quite unstable. So you need to have large data sets. Okay, so we said, okay, let's take the largest data set at our disposal. So we had 3 years. We have 3 years of tick-by-tick limit order book data, as I showed you, for all stocks on the NASDAQ. And this is, so this represents more than 100 billion observations. Okay, so this is probably, I think it's probably the largest financial data set ever studied in a paper, but I may be wrong. And I will show you that it was really not easy to study this data because the size is so large that, opening and closing a file is a non-trivial issue. So, and we separated this into 2 periods. So the first 2 years, we use it as a training set, and then we use the test set is the last year. Okay. Now, you can train the network to forecast a given quantity. So you can train it to forecast various types of quantities. So you can train to forecast how the order flow will evolve in the next time period, or you can train to forecast the price. I'm going to show you the simplest thing, which is forecasting the price move from the order flow. So you have the order book history up to some time t, and then the question is, how will the price, what is the next price move? Is it going to go up, down, and by how much? Okay, so the metric I will show in the figures is you try to forecast the probability that the price will go up at the next time it moves, given the history of the order book up to the current time. Now, you can do this at any point in time, but we chose to do this at the times only when the prices change. So if you look back at, look back at the data I showed you, so the data looks like this. So actually there are two prices. There's the best buy price and the best sell price, the bid and the ask. So we're going to look at the mid price, which is the average of these two. And so if any of these two moves, the mid price moves. So we're going to try to forecast where the mid price is going to move, up or down. And you can see that the mid price will move, in this case, if one of the queues gets depleted. If all the orders here are executed, then the best price will become the next one, so the price will move up. If all the orders here get executed, the price moves down here. So it's really a statement about the order book, but this doesn't happen at each event. So some events, for example, if I execute 100 orders here, well, this goes from 1,000 to 900. The price doesn't move. Only if I execute at least 1,000 orders does the price move. So price changes are less frequent than changes in the order book. So what we do here is we use the information, so we look at particular times that are the times where the prices change. That's typically the most interesting thing for somebody trading in the market. So this is already sampling the data. And based on what has happened up to the last price change, I try to predict the next price change. So I'm not going up to a millisecond before the next event. I may stop maybe a tenth of a second before, and I try to predict when the price will next change. So this is typically what I will show you. Okay, so you can think of this as a classification problem. Why? Because price changes are discrete. They go in multiples of 1 penny or 1 cent. And so, so here we can say, okay, the only thing we want to do is to predict whether the price will go up by 1, down by 1, up by 2, down by 2, or more than 2, okay? So if you just take 1 and 2, you get, 4 states. If you take 1, 2, 3, you get 6 states and so on. So it's a finite number of states, so it's a classification problem. So you classify histories of the order flow into up, down, and maybe up by 1 or more. So this is a typical type of application for supervised learning. So the question is, given the order flow, can you predict, can you generate, for example, trading signals saying it's going to go up or down and by how much? So that's typically what a trading signal looks like. So the state of the order book is the input. And here so just to have a benchmark, to compare, we compare it with a linear model. So it's a Cox process. So we have a discrete state space, either it goes up or down, for example. And one way to model this without neural networks is just to say, okay, it's a jump process, it can jump up or down. I'm going to learn the intensity, the probability per unit time of jumping up or down from the state variables. So I'm going to build a linear model where the intensity of jumping up or down is going to be a linear function of all the state variables up to time t, and it can depend on the past. It can be a moving average or something like that, autoregressive. So this, I learned the hazard rate or intensity as an affine function of all the variables in the order book, and then I transform this into a probability through a logistic function. So this is a logit model. Okay, so technically it's a Cox process with vector autoregressive features. So we use this as a benchmark, okay? And then the other thing is we train a multi-layer neural network, and I will describe the architecture in more detail in a second. So this is what I showed you earlier. We represent the probability that the price increases as a function of the states, where the function is a composition of linear combinations, activation function, linear combination, activation function, so on, with weights at each composition that we learn. Okay. So now here, so the neural network I showed you earlier is a static neural network where you learn some static data. There's no time dimension. When you have time series, it's a little bit more complicated because obviously you cannot, there is a time dimension in the inputs and outputs, and you're not allowed to use the future to forecast itself because otherwise you can get perfect in-sample fits. So to tackle this, Hochreiter and Schmidhuber in '97 introduced an architecture which is called long short-term memory network, or LSTM, the recurrent networks. So this is an architecture which is well adapted to time series data, where the notion of causality is incorporated into the architecture. So you have now, instead of learning a correspondence between X and Y, where X and Y are just the sample, you're now learning the correspondence between XT and YT, where you're allowed to use the X's before T to forecast YT, but not the ones after T. So this means that actually you do a sequential updating of your weights. So you can think of the neural network as a device which will take the data up to time T, learn some features, which we call here HT, and based on those features, it will generate a forecast of Y. And at each time step, you update these features by incorporating new data and the new value of the forecasted value in sample. And so it means that you update in two steps. One is you update the correspondence between the inputs at each time step and the parameters of the network, which we call here HT, the features. And then at the next, in the next step, you look at the forecast of the next value. So this means that in practice, you have to extend your calculation to the number of lags you allow. It's not unlike what you do in a linear model. If you have a linear model with k lags, it means the dimension of your matrix increases by k. And here, the dimension of the number of neurons you need increases by the number of steps because you have to incorporate this information in a causal way. So this is now used a lot in training of dynamic data, so video, sample, sound, and so on. You always have to use such a thing. Now, this is the main innovation, by the way, of the algorithms between the early 90s and now. Most of the algorithms used now in deep learning were already there in the 80s. I mean, I have a book. When I was a student, I read a book on neural networks. And when this deep learning thing started, I looked at my book and I saw that everything we see now was already there in the early 90s, except this. This was the main innovation at the end of the 90s when people started looking at non-static data. Okay, so this is the architecture that we use. So each of these is a neuron, so you need to train all the weights, and this goes back as long as you have your lags. So if you go back 100 lags, you replicate this 100 times. So this shows you that there's a lot of neurons involved, and in each layer we have 50 neurons, okay? More details are described in the paper. So you need to now train this network. And to train this network, you need to go through the data, you sweep through the time series, and at each observation point, which corresponds to price changes in our data, we update the weights. Okay, so and how is it done? Well, technically, this is done through an algorithm called backpropagation. So you can compute. So the nice thing about neural networks is that you can compute the gradient of the output with respect to the weights in the network through a recursion formula, which is the chain rule. So it's a horrible recursion formula, but it's explicit. So you can calculate the gradient of the output with respect to the weights, and you use this explicit gradient in the optimization because you don't need to do a numerical gradient calculation. Now, the gradient is a vector in dimension equal to the number of weights. So it's a vector in dimension 1 million, for example. You really don't want to store this in MATLAB in one matrix because it's going to blow up your memory. So this is where you have to be a little bit smart. So typically for this, and then, okay, the problem is you are solving an optimization problem in this dimension also, and also this can be very tricky. So the state-of-the-art algorithm used in this training is asynchronous stochastic gradient descent. So stochastic gradient descent means that you are going to calculate the gradient, but you're going to add a noise at each step. You're not going to exactly follow the gradient. So this can be thought of as a way to avoid getting trapped in local minima. And asynchronous means that the gradient vector is so large that you do not calculate, you do not update the gradient vector entirely at each step because it would be too long. You pick a random set of components in the gradient vector. You pick a random subspace in your space, and you update only in that direction. And this means you pick, for example, one of the layers. You only update the weights in that layer. You do a gradient step in a subspace, okay? And then you continue to the subspaces. So this is the type of algorithm that is scalable to such dimension. So you pick a random subspace, you update, and then you do a stochastic gradient step in this random subspace. So this is, and you iterate. Okay, so that's how it's done. Now, all this is, so the data set needs to be uploaded for each, needs to be read for each of these calculations. It's too large to be held in the memory. It's petabytes. So, in fact, it's very important to do this asynchronously, otherwise you cannot even do one step. And all this is done on GPU nodes, so the units of calculation here are always the graphical processor units, the GPUs, and these are the most performing, are the best performing appliances that can handle such calculations. So these are typically the same type of GPU nodes that you have in PlayStation or in Xbox if you play video games. Those are the best for handling these things. Okay, so the calculations I'm going to show you were done actually here at the National Center for Supercomputing Applications, Blue Waters in Illinois, where my co-author lives and works. He lives close to this thing. And this is like a computing farm where you have a large network of GPUs. There's a cloud, and we did all these computations on the cloud. So you really need large computational capacities for doing the type of calculations that I'm going to show you. But they're done only once. They're done offline. And once you train the network, then using the network for real-time forecasting, you can do it on a laptop, and it's instantaneous. It's just you do linear combinations and activation functions. So there's a big contrast in the requirements for training and the requirements for the use. Anybody can use it on their laptop. Okay, so let me show you what we do. So we use this data set for the NASDAQ to train such neural network models for each stock. So this is what I call a single stock model. So based on the history of each stock, you train the network to predict the price moves of that stock from its order flow. And then we did something that is sounds a bit strange. We pooled all the stocks together, and we trained the model on the entire data set of all the stocks, okay? And this is what we call the joint model, or the universal model. And in both cases, the architecture of the network is the same. So it means that in the joint model, it means that you show it the time series for all the stocks, but you don't tell it they're different stocks. You just, it thinks it's a long sample from the same market. Okay, it doesn't know they're different stocks. And I'm going to show you graphs which give you the out-of-sample forecast accuracy of the direction of the next price move. So it's a percentage of observations where you correctly classified the outcome. You correctly forecasted whether you go up 1 cent, 2 cents, down 1 cent, 2 cents, or none of these, okay? Now, if you do a random forecast, if you don't do anything, just throw a coin, you have to throw the coin very quickly. You have to throw 1 coin every millisecond. But if you do that, it leads to close to 50% accuracy because the price moves are, to a good approximation, quite symmetric on average. So so this is a benchmark. So if you do 50% accuracy, you're not doing anything. You can close, all this and go home. So now we're going to compare the accuracy out of sample forecast accuracy. So everything I will show is out of sample, obviously, because in sample it's meaningless. And we're going to compare the forecast accuracy with this benchmark, and then with the linear benchmark that I showed you earlier, and then between the joint model and the single stock model. Okay. So here is first a comparison with the linear model. So remember, the linear model is it's a Cox process where the intensity of going up or down is a linear function of all the state variables in the past, and it's not just the current state variables. So if you compare, so what do linear models capture? Well, linear models easily capture trends. So if the stock price is going up during the day, they can easily see that, so they can capture that. So if you forecast with the same accuracy as a linear model, it just means you're capturing a trend. You don't need the neural network to do that. Stop, go home. So you can see here the increase in accuracy of the neural network with respect to the linear model. So you can see that on average, it's something like 5%. So here, again, random benchmark is 50%. The linear model accuracy is shown here, 60%. And this is the accuracy for the neural network. So it means that you really do capture some nonlinearity with the neural network, because if it was just a trend, the linear model can do that very easily, and it can even capture a trend which is a moving, which is a linear function of state variables. So you're capturing some nonlinearity here. It's not totally useless. Okay, if these two curves are the same, it's totally useless, and again, I can stop my talk here. So it is interesting. You are uncovering some interesting feature, which is nonlinear, but again, not very surprising. We know that the time series, financial time series are nonlinear. There are nonlinear models for time series. It's not shocking to see this. So this is just a test to see if there's a big bug in our program or not. Now, this is more interesting. Now you compare the accuracy of the single stock model with the one where you pool all the stocks together, which again is not a natural idea in this literature, and then you both train them with the same architecture. Now, what we see here is the increase in accuracy of, so how much the universal or joint model is more accurate in forecasting than the single stock model. So you can see that on average, it's something like 2%, and for some stocks, you go up 4 or 5%. Okay, so it means that, curiously, this is really not obvious that if you pool them together, well, obviously you get a larger data set, but you might think, oh, but you're mixing apples and oranges. Why do you mix IBM stock time series with Google and with some industry, why should they be meaningful? Well, this shows that actually it improves. There are only a handful of stocks for which it does not improve among 1,000. So if you now look at the increase in accuracy versus the sample size available for that stock, you see that it's a pure data size issue. So stocks for which their own data set is small, when you pool all the stocks together, obviously you're going to get much larger sample size and much more diverse set of scenarios. That's where you get the highest improvement. It can go up to 6-8%. Stocks where they initially had a long and very diverse data set of histories, you barely improve when you add because they already have a large data set. So it's really a data size issue. And you see that, and this is very interesting because it means that actually this theoretical idea that there is a single price formation model which should hold for all stocks makes sense. If this is true, then all the stocks histories are samples from this price formation mechanism. They can be used to train it. Why don't we just pull them together? This is not what people do. When people estimate models for forecasting, if they want to forecast IBM stock, they will use data for IBM. They will never use data for Google stock to train the forecasting model for IBM because they think it's different. Well, this shows that it's what you gain by pooling outweighs all this reluctance to pool because they are different. They're not so different. The proof is not only you do not lose accuracy, you gain accuracy. So there's something universal in the information you get here, which is not specific to each stock. Now, this is even more interesting. So now we split the sample into two, 500 stocks on which the network is trained, and then we use this network trained on the first 500 stocks only to forecast price changes in the other 500 stocks on which it has not been trained. Okay, so it has never seen the time series for those stocks. And what we see is that the accuracy is totally comparable to the accuracy for the stocks on which it has been trained. What does that mean? It means that the relation between order flow and price change is the same for the stocks where we have trained it and the stocks where we have not trained it on. It's the same thing. It's the same for all stocks, really. So it doesn't matter if your stock has been already included in the data set or not. If it has been traded for some data sets of stocks in the same market, the mechanism is the same, and it has already learned how that works. This is very interesting because think about the consequences in practice. If you have newly listed stocks or things where you have a hole in your data set but missing data and so on. So one of the big nightmares for people handling data in finance is missing data. How do I handle missing data, newly listed contracts and so on? Well, this says it doesn't matter if it's new or missing. If you have data for other similar contracts in the market, train your forecasting model on those, and unless there's something very specific about this new stock because there's some restrictions, legal restrictions, whatever, you can use that model to forecast your new stock because it's going to work the same way. This is what it says. So here, it's out of sample both in terms of time and in terms of stocks. You train the model on stocks 1 to 500 in 2014. Then you test it on some other stocks in 2015. So both in time and in stocks. So this is, I think, the most important graph in the whole talk. So it means that this is in the learning jargon is called transfer learning. I mean, this is very nice. This literature, they invent new terms for everything, and so you have to learn all these words. But so it means that it generalizes to stocks which it was not trained on, but this is not possible unless the structure of the price formation is the same. So for me, it's really an information that, you know, what people have been assuming implicitly in the market structure literature, which is that basically it's the same for all assets and markets, is not stupid. It's actually there's non-parametric evidence that this assumption is true, which is nice, but so why does the universal model outperform the stock-specific models? Well, because you pool together 500 or 1,000 stocks, so you have 500 times more data. So it's like you have 500 years for one stock instead of 1 year. Well, of course, you're going to have a much better performance. But this only is true if there is universality, if the correspondence you're trying to estimate is the same for all stocks. And what we have is a non-parametric evidence that this is true. Okay? So and another reason is that you have much more diversity when you pull together a stock. For example, think of one stock, you have 2 years of data, but during these 2 years, nothing really happened. There's very boring. You know, the stock moves only by 0.1% per day. And then you have another stock in which you had flash crashes, you know, big moves, large trades, you know, the price is jumping up and down and so on. So now, if you only train on the first stock's history, try to forecast that stock, let's say that out of sample, you will have a crash, a large trade which causes the price to fall down by 10%. Okay. In your history, you did not have that. So there's no way the neural network is going to be able to forecast that without having ever seen such an event. But if you train it on other stocks where such events have existed, well, it's going to learn from the other examples, and then when it occurs in your stock, it's going to forecast it correctly. So there's a diversity which outweighs, this is a big argument which outweighs other learning strategies such as, so for example, when we started this, people would tell us, oh, you should use stocks in the same sector because, tech stocks are different from consumer stocks, so if you train your network, only use with the same sector, or only use stocks which have large tick or small tick and so on. And we tried all this. I'm not going to bore you with that, but we tried all this. So this is equivalent to doing ad hoc hand classification before starting the training. It turned out that these ad hoc classification clusterings did not improve the results, because they're not based on really any data. There was some people's intuition thinking that tech stocks for some reason should behave similarly. Well, tech stocks may behave similarly, but that doesn't mean the correspondence between order flow and price is different from other stocks. And what we show is that it's not different. The order flows may be different, but we're not trying to estimate the inputs. We're trying to estimate the relation between inputs and output. That is what is stable. Okay, now, next question is stationarity in time. Now, this is very important because everybody we talk to, and in the industry in particular, think that there is non-stationarity. Therefore, you should never use data from more than a month ago or so on, because it's not relevant for forecasting. Okay. Now, the data may be non-stationary, and probably it is. Okay, the inputs may be non-stationary, the price behavior may be non-stationary, but that does not mean that the correspondence between the order flow and the price change is changing with time. Okay, you take a fixed function f, and you put non-stationary inputs into it, you get a non-stationary output. Okay? That doesn't mean you need to make f time dependent. This is not true. So what we're testing here is the function f, the price formation, the forecasting mechanism. Is that thing stationary or not? And surprisingly, or not surprisingly, I don't know, it depends what your bias is, it is not. And now I'm going to show you some result, which is really what was really surprising for me. So here we look at performance on 500 out-of-sample stocks, so meaning that we train it on the first 500 stocks, and then we try to forecast the price from order flow on the other 500 stocks. But here we show this forecasting result for a 3-month period right after the training, so June to August 2015. So this is shown on the left, and on the right is the forecasting performance for the same neural network. Nothing has been updated in time from January to March 2017. So what I'm saying is that you train it in 2015, then you turn off your computer, you go on vacation, you come back in January 2017, you use the same forecasting model with the same parameters, no update, to forecast price from order flow between January and March 2017. So 18 months later. And the performance is really the same. It's comparable. There is no decay in performance 18 months after training. And this is intraday forecasting. We're talking about intraday forecasting, like second by second. So this really goes against everything I've been told, because they say, it changes so much that 1 month from now you can't use the data. Well, this means that you should use your entire data set. If you have 2 years, you use 2 years. If you have 5 years, you have 5 years. It's going to, this stability is really surprising for me. And so to check this, we looked at various things. So we increased the distance between the training set and the this table, for instance, says usually people tell you don't go back more than 1 month because the data is irrelevant because it's not non-stationary. So here what we show is that if you go back 1 month, 3 months, 6 months, you always have an increase in accuracy. It is not true that if you go beyond some level, you have so the non-stationarity could mean that you have a decay in accuracy. So it's better not to use the older data. It is not true. You always have a gain in accuracy, even if you go back by 6 months. And here what we showed is a dual type of result where you show that if you estimate, then you test 18 months out of sample, you still have a good result. So there's more detail about this in the paper, but I think that this is very important because the vast majority of time series models used in finance are estimated over short time windows due to some concerns about non-stationarity. And again, these concerns may be true that the input and outputs are non-stationary, but that does not imply that the relation between the inputs and outputs is time dependent. This is two different things, and we do not find any evidence that this is the case, that the relation is time dependent. So what we say is that once the nonlinearities are correctly modeled, the underlying model is stable and stationary months out of sample, which is what it should be for a financial application. If you have to update the parameters every day, that's not good. You should change your model. So let me stop here because I think I'm going over my time soon. So I have some other things, but I think it's less important. So let me summarize. So we've shown that if a large-scale deep learning approach can be applied to high-frequency databases of electronic market transactions and quotes, we applied this approach to US equities, and we uncover non-parametric evidence for some universal and stationary features of price formation in markets, which are found to be stable across stocks, sectors, and time. And these features capture the nonlinear relations between price and order flow in a way that is stable across time and stocks. It's the same across all periods we look at and across all stocks. We have remarkably stable out of sample accuracy for the predictions, which do not decay across time as we move farther from the training sample, and which generalize properly to stocks not included in the sample. And this, I think, has implications for how the models can be trained and estimated in finance, because typically the approach is to use recent data for the stocks or samples you're interested in, whereas here we're saying use all the data you have in the same asset class, so all the stocks on the NASDAQ will teach you something useful about forecasting for those stocks, not just the one you're trading. And for example, if you're trading a particularly illiquid stock, it might be useful to pool together a lot of these stocks and have a more interesting data set to train on. And what we show is that this is not a stupid approach. It actually improves the accuracy of your forecasts. So I will stop here and take any questions if you have.